And hello from the campus of Carnegie Mellon University in Pittsburgh, Pennsylvania. We welcome you to today's SEI webcast. Will Rust solve software security? My name is Shane McGraw, Outreach Team Lead here at the SEI, and I'd like to thank you for attending. We want to make our webcast today as interactive as possible, so we will address as many questions as we can. You can submit those questions in the YouTube chat area now. And like I mentioned, we will get to as many as we can. Our featured speakers today are David Svoboda and Joe Sible. David is a co-author of the books, The CERT Oracle Secure Coding Standard for Java and Java Coding Guidelines, and a major contributor to the SEI CERT C Coding Standard and SEI CERT C++ Coding Standard. He has taught courses in C, C++, and Java Secure Coding all over the world to various military, government, and banking groups. Joe Sible is an associate software engineer in our Cybersecurity Foundations Directorate of the CERT division. He specializes in coding and Linux systems administration. He has worked with DoD customers to ensure that secure coding rules are being followed to implement DevSecOps practices. He also maintains the SEI CERT Coding Standards Wiki. David and Joe, thanks for joining me today. And now I'd like to turn it over to Joe. Joe, all yours.
Thanks. My name's Joe Sible. As you mentioned, this is Dave Svoboda. Today we're going to be talking to you about Rust-solving software security. So I'll start giving the introduction, going over this Rust security model. Then I'll hand it off to Dave to discuss the limitations, the current vulnerability ecosystem, and stability maturity. And then I'll take it back for a conclusion. So, a little bit of introduction and background on Rust. So in traditional programming languages like C, it's easy to write code that has security vulnerabilities in it, especially memory safety vulnerabilities like buffer overflows or use after freeze. Some languages have strong type systems and other safety guarantees, think like Java, but they're heavyweight, big runtime, really slow, garbage collection causes non-deterministic performance, a lot of other downsides. So Mozilla realized this was a problem. It was steering a lot of people towards the unsafe languages. So they worked on creating a language that wouldn't have these problems in either sense, the best of both worlds in a sense. So Rust is what they came up with. It's meant to be a systems language, think competing with C++ primarily. Compiles directly to machine code like C and C++, no garbage collection. And then they did learn a lot of lessons from modern languages like functional programming, like the strong type system. Cargo is the one build system for Rust. Everything in Rust is encouraged to use it. You don't get the mess in C where some projects use auto tools, some use CMake, some use whatever other thing they feel like using. And then just a little bit of context on all the guarantees Rust is going to provide. Rust code can be put into two categories: safe, which is most Rust code, and unsafe, which is always clearly annotated as such in the source. So almost everything you'll write in Rust is going to be safe Rust. What has to be unsafe are things like the implementation of its own standard library, or if it writes code that interfaces with C code, since you can't know what C is going to do. So when you're writing safe Rust, the guarantees of Rust are something you rely on. You don't have to worry about causing undefined behavior because the language protects you from it. When you're writing unsafe Rust, then all Rust guarantees become obligations for you instead. In unsafe Rust, it's your job to make sure you don't let safe Rust break any of those rules. And then unsafe Rust that does that correctly is called sound. And if it does it wrong, it's unsound, and soundless bugs are that category of bugs.
So what you're saying basically is unsafe Rust kind of gives you the same power along with the same danger that you get with C. And then safe Rust gets you, less power, but also less danger. Is that a good way of putting it?
Right. So the idea is you spend as little time in unsafe Rust land as possible, and that gives you the maximum safety guarantees.
Do what you can just to make Rust just a little bit more powerful without making it more dangerous in unsafe Rust, and do everything else in safe Rust.
So the big feature that Rust brought to the table in the world of programming languages is its borrow checker. So in Rust, every object always has one owner. When you create an object, you own it. And then you can either give ownership away when you pass it moving it to another function, or you can let other code borrow it. So every borrow is either immutable, which means read-only, or mutable, which means read-write. So there can be as many immutable borrows as you want at a time, but there can only be one mutable borrow. And if there's a mutable borrow, there can't be any immutable borrows at the same time. And then the other key rule is all borrows have to be returned before the object can go away or have its ownership transferred away. And those rules together are basically the core of every safety guarantee Rust offers, as we'll see in the next couple of slides. So the security model of Rust now. So as I mentioned before, C and C++, memory unsafe, really easy to cause buffer overflows, use after free, a lot of other vulnerabilities too. Java does all the checks at runtime. So if you go out of bounds in an array, for example, in Java, you're going to get an exception at runtime. So no security vulnerability, but your program still crashed in production. One of the advantages of Rust is it catches most of these kind of mistakes at compile time before they can become bugs. So here's an example of a C++ program that has undefined behavior in it. So it creates a vector, starts iterating over it, then appends an element to the end of the vector, and then continues using the iterator. So when you append an element to a vector, it might need to reallocate. And if it does, then all iterators are invalidated, which makes that final line undefined behavior from referencing freed memory. And neither GCC nor Clang will give you any warnings when you compile this program. Undefined behavior will just happen at runtime. It might just give you the wrong answer. It might segfault, or it might even work fine when you test and not break till it gets to production, or until you change some other unrelated bit of code somewhere else. That's what makes undefined behavior super dangerous. It's unpredictable and hard to find.
Unpredictable, undefined behavior is sort of the standard committee's way of washing its hands and saying, you know, whatever you do now, you're on your own. We're not going to make any more guarantees of what the program can do.
So here's an equivalent program written in Rust. So you can see the similarities, also creating a vector, starting to iterate over it, pushing an element onto the end of the vector, and then continuing to use the old iterator. So this has the same problem as the C++ program. That iterator is invalid there. But this is safe Rust, so there's no undefined behavior. So Rust catches this at compile time with this error.
Colorful.
So what it's saying here is, when you created the iterator, you immutably borrowed the vector. And then when you push an element into the vector, that mutably borrows it. But the immutable borrow is still there since you used the iterator afterwards. So this would have an immutable and a mutable borrow at the same time, which you said wasn't allowed. So Rust tries to explain that in detail, why that's not okay and why it could be a problem.
So the error message it's giving you is kind of based upon its own borrow checkers model. To understand this error, you have to understand the borrow checker.
Right. So here's another example. This time, this is a C program with undefined behavior. So it takes a string and puts a copy somewhere in the heap, then immediately frees what it made, but goes on to use it anyway. So use after free, again, undefined behavior, common source of security vulnerabilities. So in this case, this program will probably happen to work most of the time until you change something else. It could also print garbage. It could also segfault. And my kind of rule of thumb for thinking of undefined behavior is it works until it needs to.
Yes.
And again, no compilers will catch this with their standard suite of warnings. Same bug in Rust. Creates a copy of the string on the heap, immediately deallocates it, then tries to print it. Again, that's use after free. And again, Rust catches us at compile time. So drop is how you deallocate objects in Rust. When you pass something to drop, you give ownership away to drop. And if you remember, the other rule of the borrow checker is all outstanding borrows have to be gone before you give away ownership of an object. So here it's saying print line was going to borrow X even though you don't own it anymore. That's not okay. And again, there's a lot of details in this error message explaining that and exactly why and how to get more information if you're confused.
And again, to understand this, you have to understand the borrow checker's way of understanding things. I mean, it occurred to me that it would be nice if it just simply said use after free error, but it gives you what it's giving you is basically in terms of the borrow checker's mentality.
Right. And part of the reason for that is maybe the thing you moved ownership to did something other than free it and wants to keep the message generic. And that is one thing that the Rust compiler authors realize is this whole thing with ownership and lifetimes and borrowing is new to most programmers. So they really went out of their way to make their error messages as detailed as possible and tell you exactly how to get more information if you're still confused.
Yes, that is helpful.
So a couple of other mistakes that Rust helps you avoid is Null. The existence of Null is the billion-dollar mistake in programming. The idea is there's probably been at least $1 billion worth of problems and lost productivity caused by Null.
Mm-hmm.
So in languages like C, any pointer can be Null. In Java, any reference can be Null. And the problems that causes are some variables you never want to be Null. Nothing stops someone from making one that anyway. And some variables are, but nothing stops you from using it without a check. So what Rust does is they say, by default, no types can have any equivalent of Null. If you want something to be optional, you have to wrap that in option.
And option is a special type.
Right.
Option is kind of the only type that allows null.
So it's not even that it's special, it's just a generic sum type, which is a concept that came from functional programming. So the idea is every variable needs a value of its type. Option is either a unit type just called none with nothing in it, or it's sum, S-O-M-E, sum this time, with your value in it. Mm-hmm. So the compiler enforces when it's not option, there must be a value there. And when it is option, your code has to handle the case of it being sum or none. So you can never make a mistake like you can with null that would result in a null dereference.
And Rust didn't invent this. As you said, it comes from functional programming, and it exists in several other modern languages like Go and Swift. But yeah, it hasn't made its way into Java and C yet.
Well, this is actually one thing Go is still lacking, but yes, Swift does include it.
Okay, you're right.
And yeah, this is definitely an old concept. Haskell, I think from 1999, has that concept. They call it maybe, but it's the same thing as option. Mm-hmm. So concurrency is the other big kind of mistake that Rust protects you against. So just about every programming language has the concept of data races. We have two different threads, both accessing the same memory at the same time. So in C, that can cause all kind of weird things, like you wrote variables in one order, then the other thread sees the writes happen in another order. Or you write a variable wider than a word, another thread might see half of the write and half of the old value. All kinds of problems like that, all undefined behavior. So in Rust, the borrow checker prevents you from this because if one thread has the mutable reference to that variable and can change it, you know that no other threads can have an immutable reference to it.
Because it's only one with a mutable borrow.
Right. And then when you do need to access things from multiple threads, that's where there's wrapper types like mutexes. And sure, other languages like C have mutexes too, but you can forget to use them in C and your code will still compile, and it will just have a race condition bug and do the wrong thing. Mm-hmm. Whereas in Rust, it can use like token types built around the borrow checker to make sure that you can't access the variable if you forgot to take the lock or the mutex. So that wraps up my section. So Shane, do you have any questions for us before I turn it over to Dave?
We do, Joe. One from Walter asking, we see concepts from functional languages becoming part of object-oriented languages. For example, pattern matching, C#. Do you think that some of the concepts from Rust might be taken up by other languages?
Yeah, I definitely think so. The bar checker is the big one. I know the newest versions of Ada recently incorporated that.
I recently read a research paper about an attempt to port the borrow checker to C++, so it could be used to enforce C++ code. And they ultimately decided that there was too hard. There was too many differences between the fundamental unchangeable parts of C++ and the borrow checker. So you're unlikely to see a borrow checker in C++, although you probably will see safety models similar to that.
And then just a general question, what kind of programs can you write with Rust?
I would say that given that Rust forces you to worry about the borrow checker and worry about your memory management, you're going to be using it to write the same kind of programs that C is ideal for right now. So think of OS kernels, think embedded software where the size of the program is critical, the speed is critical, and it should take as little memory as possible. Remember, while the borrow checker enforces safety requirements, it's only at compile time, and your program at runtime runs pretty much with the same speed and light footprint as a C program does.
Great. Next one we have from Sushil asking, has any modeling language been linked to Rust for auto transformation of the model into code?
I don't think I know the answer to that question. I'm going to bet that yes, it has been done. It's certainly pretty easy to take some modeling language and as a front end and assuming that it auto generates C, you could probably just change it to auto generate Rust. But I don't yet know of a project where that's been done.
Yeah, I'm kind of echoing what Dave says. I don't know for sure if that's been done either, but there doesn't seem to be any reason it couldn't have been.
Okay, we are caught up on Q&A, so we can go on to David's part. Thank you for that.
Thanks, Shane. Okay, so Joe's already given us a good overview of Rust and what the security model protects us from. And now I'm going to talk about the limitations of the security model. Every security model is limited. Partially, it's limited because everyone has a slightly different notion of what they want out of a security model. So there's no way that Rust security model could satisfy everyone. It might satisfy Joe and not satisfy me, or vice versa. Or more likely, it tries to satisfy the things that Joe and I have in common, and that means that we're both slightly unhappy with it. We both would have things it doesn't satisfy. So we've already talked about the borrow checker. I'll show you some borrow checker limitations in a little bit, places where the borrow checker is problematic. But the borrow checker also is limited scope. It's limited to memory safety and concurrency safety. And with concurrency safety, it's limited specifically to race conditions, which we pretty much define as concurrency safety over memory, to make sure that no memory is accessed by two different threads at the same time. But you could have other kinds of race conditions, such as files being accessed over by two different threads at the same time, and Rust does not handle that. So there's no reason why a Rust program and a C program couldn't have a race condition over a file. There's many other types of security problems, and you can read all about them in our cert rules or in, say, MITRE CWEs. SQL injection is one such type. There's deserialization vulnerabilities. Those are nasty in Java and Python and Ruby. And then you can have other such programming bugs like floating point exceptions. If you expect to get the value 5.0 and you get 4.999995, well, depending on what you're doing with that value, you can have some serious problems, and Rust does not help you with those. And Likewise, of course, there's lots of deprecated and obsolete algorithms on there. MD5 is one such example. When I first heard of MD5, I didn't even think of it as a cryptography algorithm. I was just told, did your download complete properly? If so, then you should have the MD5 hash, the following MD5 hash. And back then people were using it just for doing checksums and not for crypto. But well, if you're doing it for crypto now, then you are using obsolete technology. You are living in a state of sin. Go forth and sin no more. Okay, so I'll move on to an example of the limitations of the borrow checker. Now, as Joe explained, the borrow checker is designed to prevent any insecure source code from compiling. So when the borrow checker has errors or bugs or warts, whatever you want to call them, it errs on the side of caution. And by that, I mean it takes a perfectly valid program that would not have undefined behavior, and it forbids the program from being compiled. So what I have here in the slide is an example of C++ code that is perfectly safe and fine. It's very similar to Joe's example. In this case, we're iterating over a vector, and instead of adding a new element to the vector, we're just changing one of the elements of the vector. So whereas adding an element to a vector in C++ causes any iterator to become stale, changing a vector's element does not. You can change elements willy-nilly, and as long as this element number is the same, your iterators are still good. So this program compiles properly and runs and does exactly what you expect. The analogous Rust program, however, fails to compile. And again, while it looks to you and me that this program is well defined, it would work properly, it violates the borrow checker because, again, we are doing an immutable borrow on the second line of actual code and then a mutable borrow on the fourth line of actual code, and this is forbidden. So the borrow checker will stop you and not allow this program to compile. So in other words, the borrow checker kind of gets in the way of what would otherwise be perfectly fine working code, because the borrow checker's model is limited. It is limited in that it's not limited in that it ever allows insecure code to compile. It's limited in that it sometimes forbids secure code from compiling. Fortunately, there are several workarounds. If you really want to compile and run a program that does this stuff, you can do things such as wrap your vector elements in a cell in the cell class, or you can use the split at mute class, or you can work with indices rather than iterators. So there's several ways to skin this particular cat. It's just that the way that we've done here violates the borrow checker's limitations.
Yes. And then it's worth mentioning all those workarounds are in safe Rust. None of them open you up for the possibility of undefined behavior or any bad things like that.
Right. So this particular program can be rewritten correctly. It's just that rewriting the program in this way shows that the borrow checker imposes some excess limitations on the programmer. So what I have here is simply an overview of the various security classes of security problems. And as you can see, Java and Python provide a bit more security guarantees than C provides, and Rust provides a bit more on top of those, because again, the goal of Rust was to obtain the best of both worlds, the security that you get in Java and Python, but along with the performance that you get in C. So I'll simply note again that the security that Rust provides is not absolute. You still have third-party code as problems. The integers, you get some protection against integer overflows because Rust can sometimes detect them. I believe that's a switch you have to turn on when you're building Rust code. So again, it's not a panacea, but it is a step in the right direction.
A few points worth bringing up here. So for integer overflows, there's two kinds of problems people think of when they think of that. One is like unsigned integers in C, where it wraps around and isn't undefined behavior. It could just be unexpected. The other is like signed integer overflow in C, which is undefined behavior. In Rust, you're always safe from the undefined behavior. The only question is whether you want wraparound to happen or the error to be caught. The other thing I wanted to call attention to is memory corruption in languages like Java and Python. They have escape hatches that will let you be memory unsafe too, just like Rust does. In Java, think JNI or sum.misc.unsafe. In Python, think C types.
Right. In fact, all three languages. So Rust doesn't exactly have an escape hatch outside of Rust. You can't like say, I'd like to write this part of Rust in C or assembler. But Rust does have unsafe Rust when you want to do something that's unsafe.
Well, I think they did recently stabilize inline assembly, actually. And yes, that's definitely unsafe blocks only.
Right. It's unsafe code. So to me, I mean, this is interesting to me in that Java and Python, if they want to let you write unsafe stuff, they'll let you drop down into C. And of course, the Java developers are not responsible for the C language, and neither are the Python developers. The Rust developers are responsible for unsafe Rust, but they're not responsible for what happens in C or assembler.
Right. So if you want to call C from Rust, you have to write the unsafe code that does it. And then any undefined behavior is your responsibility.
Right. So unsafe Rust is simply them taking some responsibility for unsafe code that you write. Whereas if you go into C or assembly, yes, you're on your own. Okay. So I'll go ahead and ask if there's any quick questions before I move on. Shane?
Yeah, we got one from Walter, David, and that is there some cargo tool like Clippy that would detect insecure code in Rust?
I actually did talk about this coming up, so I'll encourage Walter to stay tuned. I will have a slide about static and dynamic analysis for Rust code shortly.
Okay, and we got one more from Sushiro asking, can all the unsafe/insecure usages identified in this presentation be prevented through the concept of a safer subset of Rust, for example, as in Misra C?
Well, safe Rust already is that. It does prevent all the bad things we've talked about. They're already all only possible in unsafe Rust.
Right. There are some things like SQL injection that Rust doesn't prevent. And if you want to prevent that, then you might stay away from working with a database. If you have to work with a database, then our advice is simply the same advice we would give if you were using Java or Python or C, which is don't just pass a string to your database. Use a prepared string or both Java and Python have
statements.
Prepared statements. That's the phrase I was thinking of. They have methods for safely building SQL statements with sanitized data so that you can avoid SQL injection. And Rust has these things too. Rust just isn't better than Java or Python at preventing SQL injection.
To the first order approximation, everything that Misra C protects you from in C, safe Rust already protects you from.
Okay, so you just touched on this. So this might be Daniel's question. It says, Daniel asked, the Rust type system can be extended by third-party libraries for handling non-supported checks like SQL injection.
I mean, in principle, you could write a compiler plugin to do whatever you wanted, or try to build a SQL library that only lets you use parameterized queries, yes. Neither of those things are inherent to the language, but it's definitely possible, and there probably already are third-party crates that do that.
Okay, we're caught up. Thank you, guys.
Thank you, Shane. Okay, so in this section, we're going to basically, this section is designed for system administrators and users, people who are not Rust developers. The argument being that your system has to have some Rust program in it, and you're concerned about the software, about the safety and security of that software, and you're not a Rust developer, so you can't necessarily fix any vulnerabilities yourself. So good news, of course, is that Rust is getting more and more popular. It's been accepted into the Linux kernel. That is to say, they will let people submit Rust device drivers as of version 6.1. It's
6.2.
6.2, right. It's also been added to UEFI, so it'll appear in Microsoft Windows shortly. There is, of course, the Rust C compiler, which is a front end to the LLVM, and the GCC folks are actually writing a Rust front end to the GCC tool chain. So this just simply shows that Rust is getting more and more adoption, but that means that as it gets more and more adoption, that the attack surface of Rust software is growing, and there may soon be there may be Rust code on your machine that is insecure, or there might soon arise some. So how do you deal with that? So we did a quick search on MITRE's website for CVEs that involve Rust, and we came up with 400 hits of CVEs, vulnerability reports that involved Rust code. And these ran the usual gamut of security problems such as unsafe deserialization. They did include use factor free and out of bounds writes, which are memory problems. Those should have been caught by the borrow checker. Obviously, these things escape the borrow checker, and it's an open question as to why. You can look at those individual CVEs if you want. It's possible that there was a bug in the compiler. More likely, these might have been unsafe Rust, or they might have been, Rust interacting with C in some unsafe fashion.
Right. And most of these, I can say it turned out, were because of the use of unsafe Rust. Virtually none of them were compiler bugs or soundness bugs that led to these.
Okay, so the point being, of course, that also since these were a couple months ago, then it stands to reason that many of them will have been patched by now, or by the time that you hear this. So consequently, the fact that Rust Rust is less vulnerable than or Rust programs are less vulnerable than C programs, are less likely to be vulnerable, but clearly it can still happen, and so we therefore need various analysis tools such as static and dynamic analysis. So Rust is a fairly new language, and therefore what that means is that the I guess you might say the market or the set of current analysis tools is still very embryonic. I have here two tools, Rudra and Miri, which are static and dynamic analysis tools for Rust, and they do find some things. They find very little. Part of the reason they find very little, of course, is that the borrow checker in Rust catches many errors that are caught by static analysis in C and Java. So a lot of the work that static analysis tools have to do in older languages, they don't have to do in Rust because the borrow checker does it for them. But that means there's still some things that they can do, and that so they still have to check for some things like integer overflows, and therefore we have these tools available for now, but they're still largely research and beta quality tools at this point. One other thing you can do with Rust is try to reverse engineer Rust code using Ghidra or some other decompilation mechanism. I will say that these tools are also in an embryonic state. We have a lot of experience with reverse engineering C code, but Rust does some things differently than C on the assembler level. For instance, they might reorder their struct or class members in order to compact memory more, and C doesn't have to do that. So there are challenges in terms of static and dynamic analysis and reverse engineering tools. One thing I'll conclude with here is simply that Rust is also starting to be used for malware, and this might concern you simply because that means that they're going to make there's going to be more strong secure malware out there, and that's a fair point. I will add, however, that it's a fair point, but it's a less scary point than if the malware writers were not using Rust at all and they decided that Rust was insecure and not worth their effort. So, use Rust because the malware users are doing it. All right. So, Shane, I'll turn it again to any questions before we move on to overall stability and maturity.
Or Tim chimed in with asking, I heard something about Polonius that should be able to allow more than the borrow checker today to eliminate the limitations you mentioned. Do you know more about this current status?
I think I've heard the name Polonius. I don't know anything else about it yet. Have you heard anything, Joe?
It sounds familiar to me too, but I cannot recall if it would fix the problems in this presentation or not.
Okay, that was all the only thing in there as of now.
It's good to know that there are people, at least, that these are problems that people are paying attention to and trying to solve. Hopefully next year we'll be able to say, the field of static analysis is a little better now thanks to this new tool or thanks to this new project. This is the nature of technology. Things get better. Okay, so the last major section I wanted to talk about was stability and maturity. And well, I started off this section thinking, what the heck is maturity? To me, maturity simply means a language is young, and it simply means that my boss doesn't want me programming in it because it's immature. And so I basically sat down and came up with a list. And the list is here of aspects of a language that would contribute to it being considered mature. So some of these are bureaucratic, that there's a committee of some sort that maintains a language, that the committee employs some sort of transparent mechanism for issuing releases to the language, and that the committee does some also surveys how widely used the language is. A lot of that became easier in the open source era because we now have open source repositories like SourceForge and GitHub, and there's further more technical items such as a reference implementation, or a compliance test suite that can tell you if your homegrown Rust compiler is actually compatible with Rust C. And likewise, a repository of third-party libraries. If you write an open source Rust library, where can you publish it, or where can you publish a C library? So with these eight metrics, I then applied them to C, Java, Python, and Rust. And as you can see, most of these metrics are supported by all four languages. But you see an interesting set of gaps. Towards the bottom there, you'll see that C and Java are stronger when it comes to the bureaucratic side. They're stronger in terms of having official established committees. C Standards Committee is a subgroup of ISO, and Java is a subgroup not of ISO but of Oracle. Actually, the Java community process is quasi-independent of Oracle, and the relationship between them is murky, and that's all I can really tell you. However, Python and Rust excel not so much in the bureaucratic side, but in the technological side. Both Python and Rust have official repositories for third-party code. Joe already mentioned Crater for Rust.
Cargo.
Sorry. Cargo, Crater. These words all start to sound alike after a while. But Rust also has this interesting survey technology, Crater, which I want to talk about a bit more, because what they do with it is every now and then, I'm not sure if it's nightly or weekly, it basically iterates through all of the published code, open source code, either on GitHub or crates.io, and it tries to build all the Rust code there and tries to run internal tests. And they use this to test new features of the compiler. And what they decide is if the new compiler, a test fails, but the test worked on the old version of the compiler, the stable version, then they figure that they've either found a major compiler bug that they can fix, or they may decide that Well, they may realize that there's some broken code out there, Rust code on GitHub or Crates.io. Now, the nice thing about that is that if they still want to run with their to upgrade the compiler and break the code, they can at least contact you. You know, if it's your code, they can contact you and saying, "Hey, your code is using this version of Rust, of the Rust compiler. Your code will no longer compile against the beta version. Would you like our help in modifying your code to work with to stay up to date with modern Rust?" So this is a way of stability, of achieving stability, in that, if your code breaks and it's open source, you'll get some help from the Rust community.
And then it's worth mentioning, even that's the less common outcome. Usually, unless they find a soundness bug in a standard library, they're not going to break it and then come to you to help fix it. What usually happens when they find breakage like this is they realize they introduced one by accident, and they'll fix that before the next stable release, so no change to your code is needed at all. Right.
This is usually a way of just detecting bugs while they're in Rust C itself. So another point for Rust stability is that most new languages that add new features as they go along, they will have incompatible features or platform-specific features that they'll encourage you to use. Some vendors, who shall remain nameless, have often used this as a way of locking people to using their own platform by encouraging you to use platform-specific extensions. So Rust has the same problem, and I use the term loosely because obviously for some vendors this is sort of an asset at vendor lock-in. But Rust basically forces you to use the following syntax, which is in the lower corner of this slide, if you want to use a unstable feature. So while you can use experimental features, you can't do it without being made aware of it, that you're potentially doing something unstable.
And one thing I'll add is, in addition to needing to use that feature annotation if you want to use unstable features, you then also need to build your code with a nightly compiler rather than a stable one. So you're really opting into instability if you want it, so it's never going to surprise you.
Right. It's very hard. It's considerably harder to use the unstable nightly Rust compiler than an unstable nightly, say, Java or Python interpreter. One last thing I'll mention here is that the Rust.io, or the package repository, has simply made a promise, at least in that they are promised not to unpublish any stable code, any stable Rust crates. So you don't have to fear relying on a crate and suddenly the crate disappears and you can't use it anymore. Joe and I both remember the LeftPad fiasco, which occurred in 2016, where the JavaScript repository, I think it's NPM, right? They took down, at the request of the author, they took down about 11 lines of JavaScript code, which wound up breaking about half of the internet. And Joe and I have also encountered this problem in using a certain Ruby on Rails gem as well. So this problem can occur in repositories if they allow code to be unpublished. But Rust just, the crate forbids that from happening in Rust. If you publish something in Rust and it becomes stable, then it's up there and you no longer have the right to withhold it. You can decide not to publish any more crates if you want, but the ones that you posted up there, well, they're there for good from now on. You can mark them as deprecated, but you can't remove them.
And then if you do mark one as deprecated, that'll keep packages from adding it that didn't use it before, but it'll always continue to be available for whatever already has used it.
Right. Okay. So as a quick conclusion of the maturity, you have actually, our conclusion was that there's two levels of maturity for Rust, depending on whether you're working with open source Rust code or proprietary closed source code. If you're doing proprietary code, that is, you're not sharing it with anyone, or you're sharing it only with a paying customer, then you've got about the same level of maturity that you have with Python. That is, it's it's fine for the version of Rust that you're using. However, it might possibly break under new versions of Rust. It's unlikely. They'll try to prevent that kind of thing, but the Rust developers, can't help you or detect the breakage in your code if they don't have access to it. However, if your code is open source and you publish it on GitHub or Crates.io, then your maturity level goes a good bit higher, because you can add tests to simply say, if this test ever breaks, then that's a bug in the compiler, or you're changing the compiler in an incompatible way.
Right. In effect, if you make your code open source, it becomes part of Rust-C's test suite.
Exactly. It becomes part of the test suite for Rust-C. So this gives you a level of stability maturity that's greater than Python. It's still not quite at the level of C or Java yet. And the reason I give it lower marks than I give for C or Java is because right now, Rust-C is a very good compiler, but it's the only one. If you want to compile Rust code, you have to use Rust-C. Eventually, Rust will have there'll be a GCC front end, and that will be a second compiler, and that will increase stability a bit more, because GCC, or whatever they call their Rust front end, will have some variations between what it accepts and what Rust-C accepts, and that will basically force more stability. It will force them to agree on what parts of the language are specific to the Rust-C compiler and what parts are general. So it will force them also to write up a written specification, and probably have a test suite as well that both GCC and Rust-C conform to.
And I'll also point out C and Java aren't perfectly stable either. Just as quick examples of each. In C, removal of getS, even though it was super dangerous, was still technically a breaking change. Removal of K and R function definitions, another, because there's edge cases where they can't be replaced, even if they weren't, still technically is. Java, the big one was back in Java 9, when they added the module system that broke a lot of uses of reflection, needed new flags like add opens. So the benchmark here isn't perfect.
Right. Well, perfection is an impossible dream in this world. And I'll just simply add that I can still compile programs that use getS with GCC. So even though it's no longer in the language, it's still supported by the compilers for as long as they want to. So, are there any more questions before we move on to the conclusion, Shane?
We had one from earlier, David, asking how many CWEs apply to unsafe Rust?
So, right, when we did the search, there was about 400.
I think you said CWEs, not CVEs.
Oh,
right?
Sorry. So, yeah, CWEs are common weakness enumeration, which are categories of vulnerabilities. CVEs are common vulnerability enumeration. I'm not sure. Yeah, the two acronyms are very similar and very confusing. CWEs are language agnostic. They're supposed to apply to every language. And there are a few that are specific to certain languages, but so the question was how many CWEs correspond to unsafe Rust?
Correct.
So it would stand to reason that the ones that are specifically about out of bounds memory reads or writes would not apply to Rust. You're losing a handful right there. There are, I know that I forget the numbers. There are ones about data races that would also not apply. Let me think a moment.
I also think any that are about pointers in particular will only be applicable in unsafe Rust.
Right, use that for
Rust,
free.
Yeah, because safe Rust prevents all mishandling of pointers.
Right. So I know that I just discovered that there's a CVE number 1135 or so, and the last I knew that CVEs went up to 1,000. I'm guessing there's only about 1 to 200 CVEs, but the number keeps leaping up on me and growing. So any answer I can give you now will probably be obsolete next month.
All right, we are caught up in the queue. So if anybody has any further questions, I know Dave's going to go through the conclusion now. Feel free to get them in there. Yep.
Actually, I'm going to turn the conclusion over to Joe.
Okay.
Yep, so I'm going to wrap us up here. Thanks, Dave.
Mhm.
So yeah, key takeaways. Yeah, Rust is a lot safer than C. It's not perfect. There's some kind of vulnerabilities programming languages will never be able to solve, like if there's some administrative function and you forget to check to see if the user's an administrator, no language is going to catch that kind of thing. Tooling, it's catching up really fast for how new Rust is compared to C. Like 10 years old versus 50, that's a 40-year difference. You wouldn't know it based on how close the tools are already. As was mentioned before, there's a lot of places like Linux kernel, Windows kernel, even Firefox using Rust in production now. I'll also mention one thing that's going to lead to a lot more Rust in the Linux kernel is once GCC supports Rust well enough, then it'll work on a lot more architectures, and then it can be used in a lot of the architecture-independent places in the Linux kernel. Right now, LLVM supporting fewer is kind of a blocker on that. Companies like Amazon and Google are using Rust in production too. I think this is enough examples here to show the world has accepted this as a commercial production-ready language. It's not an experimental thing anymore. So that's basically all we had. So if you have any final questions, now's the time. If you have any later, email address on the screen, info@sei.cmu.edu. It'll get routed to one of us.
And I would like to give one quick shout out to Garrett Wasserman, who helped us assemble this presentation. In particular, he was responsible for the Rust security in context, talking about static analysis tools, CVEs, and so on. So thank you, Garrett.
David, Joe, great discussion today. Thank you very much for sharing your expertise.
It was great to be here, Shay. Thank you.
Thanks.
And we'd like to thank you all for attending today. Upon exiting, we ask you hit the like button below the video window and share the archive if you found value. Also, you can subscribe to our YouTube channel by clicking on the SEI seal in the lower right corner of the video window. Our next webcast will be August 9th. And the topic will be what's wrong with ROI for model-based analysis of cyber physical systems. Registration information is available on our website now and will be emailed out as well. As David and Joe mentioned, any questions from today's event, please send to info@sei.cmu.edu. Thanks, everyone. Have a great day.